Welcome to this explainer where we're digging into the case of the changing states. Have you ever looked at a burning log or, even just your own breath on a cold day and wondered what is actually happening at the molecular level? Well, today we're going to decode that hidden language of matter and investigate the profound line between physical and chemical changes. Let's kick things off with a bit of a mystery. Imagine you're boiling a pot of water for pasta. You crank up the heat, and pretty soon, violent bubbling starts, gas is escaping, steam is rising everywhere. It looks super active, right? But here's the question. Are you actually witnessing a chemical reaction? Just hold on to your answer for a second, because to figure this out, we need to establish some baseline rules of matter. So here's the absolutely crucial distinction we need to make. In a physical change, a substance might change its appearance, sure, but its molecular identity, that stays completely untouched. And it's usually reversible, like melted ice can easily just be frozen again. But a chemical change? That is a total irreversible transformation. Bonds between atoms are literally ripped apart and completely new ones form. You start with one thing, and boom, you get an entirely different chemical identity.
You see, a physical state change is basically the ultimate molecular disguise. Take water, for instance. You can freeze it into solid ice, melt it into a liquid, or boil it off into a gas. It looks drastically different each time, but if you zoom way in, it's still the exact same H2O molecule at its core. Literally no chemical bonds were broken. The molecules just, changed how they're spaced out and how much energy they have.
And that brings us right back to the answer to our mystery. Boiling water? Total red herring. Those bubbles are just a physical state change. It's just liquid water spreading out and becoming water vapor. But contrast that with dropping one of those fizzy bath bombs into your tub. That fizzing happens because the citric acid and sodium bicarbonate are actually mixing with the water and undergoing a true chemical reaction. So those bubbles, that's a brand new substance, carbon dioxide gas, literally being born right there in your bathtub.
Now, without a fancy microscope, how are you supposed to spot a true chemical change? Well, you got to look for the physical clues. Does the mixture suddenly change color? Is there a weird new smell? Does it spontaneously get hot? Or maybe drop in temperature like one of those instant cold packs? Or maybe it emits light. Think of snapping a glow stick. And super importantly, watch for an unexpected change in physical state, just like our solid bath bomb suddenly generating gas. These are the classic telltale fingerprints of a chemical reaction.
Section 1. The language of detectives, tracking atomic evidence with chemical equations. So to track all these microscopic interactions, scientists rely on chemical equations. Think of them as basically before and after snapshots of a reaction. To write one, you list your starting ingredients, the reactants, over on the left, and your newly created products on the right. Then you have to balance it. Why? Well, because of the law of conservation of mass. The universe is a very strict accountant. Atoms are never magically created or destroyed, they only rearrange themselves. So we add coefficients until both sides match up perfectly. And finally, we indicate the physical states of matter.
And it's that final step where our focus on physical states really shines. We drop these specific tiny state symbols right next to the chemical formulas. A lowercase s for solid, L for pure liquid, G for gas, and AQ for aqueous, which just means it's dissolved in water. Now these tiny little letters are absolutely critical. They act as the official record of what state the matter was in right before the reaction and exactly what new physical state it took on afterward.
Let's actually put this all together. Take a look at this balanced reaction between tin oxide and hydrogen. Notice those state symbols tucked into the parentheses? We're starting with a solid and a gas. They chemically react. All those bonds break and reform, and boom, they produce a pure solid, tin, and a gas, water vapor. Looking at it this way, those state symbols definitively prove exactly how the physical states transformed right alongside the chemical identities.
Moving on to Section 2, Catalysts, the ultimate cheat code. Okay, so we know the strict rules of chemical reactions by now. But what about bending them? Enter the catalyst. A catalyst is a substance you add to a reaction to speed things up, sometimes literally by millions of times, or to lower the temperature you'd normally need just to get it started. But here's the real magic trick. The catalyst itself is never actually consumed. It just facilitates the change and walks away totally intact. Now, we've used natural catalysts for millennia, like yeast enzymes in bread dough. But today, modern science engineers them to do so much more. So, How does this chemical cheat code actually work? Well, every reaction has a sort of hurdle it has to jump over to get started, which we call the activation energy. A catalyst essentially just lowers that hurdle. Plus, they have this amazing superpower called selectivity. They basically act like microscopic traffic cops, forcing a reaction to produce exactly the product we want while cutting out the unwanted, toxic byproducts. By manipulating these energy barriers, catalysts have literally become the secret engine driving the modern world, giving us things like biodegradable plastics, life-saving pharmaceuticals, and even highly efficient solar fuels.
All right, so we've decoded the ultimate molecular disguise of physical state changes, we've tracked the atomic bookkeeping using chemical equations, and uncovered the crazy rule-bending power of catalysts. So, I want to leave you with a bit of a challenge. Look around the room you're in right now. Can you spot one physical change and one chemical change happening? And just think about this. Every single breath you take, every thought you have, is driven by millions of microscopic chemical reactions and catalysts firing off right at this very second. You are, quite literally, chemistry in motion. Keep observing, and I'll catch you next time.